Okay, all right. We'll start now. Good afternoon, everyone. So I welcome you all for the one more session on problem solving for the NPTEL course Computational Fluid Dynamics. The course code is NOC25H18, and we are almost into week 10. And the course instructor is Professor Sreenivas Jayanti sir from the Department of Chemical Engineering, IIT Madras, and myself, Ankara Kartiga, research scholar from the Department of Chemical Engineering, IIT Hyderabad. So in today's class, we will be solving problems related to week 10, so that will help you in submitting your week 10 assignments. So we will start now. Uh, as you know, this is a 12 weeks course, and we have seen whatever things we require from the basics. And week 1, it was introduction about the calculation of flow in a rectangular duct. And week 2, it is about calculation of fully developed flow in a triangular duct. So in week 1, it was about how we are calculating the flow in a rectangular duct when we use the finite difference approach. And in second week, it was about finite volume method. So that gave us an introduction about how we will split the equations. I mean, how we discretize the equation and use those equations in solving for the required flow field variables. So in week 3, it is about derivation of equations governing fluid flow. Basically in CFD, what we do is that we discretize the domain into smaller regions and we solve for the flow equations in all those regions and get the solution. So what are all the equations we solve? If it is a generic fluid flow problem, we solve for the continuity equation and momentum conservation equation. So in addition to this, if there is any external heat transfer or mass transfer or chemical reaction taking place, we go with those additional equations as well. So it is about derivations or derivation of equations governing fluid flow and the detailed equations for incompressible flow along with the boundary conditions we have seen in week 4. It is nothing but incompressible flow. We have that Navier-Stokes equations. Along with that, we apply the boundary at the boundary points. For example, if we are talking about a fluid flow in a circular pipe, we give the inlet velocity, that is one boundary condition. We give no slip wall, that is one boundary condition, and at the other end we give pressure outlet, that is one boundary condition. So basically we are specifying the values at the boundaries in terms of inlet, wall or outlet. All along all these regions we specify the values, that is known as boundary conditions. And we have a basic type two type. Basically we have two types. One is Dirichlet boundary conditions and the other is Newman boundary conditions. In Dirichlet boundary condition, what we do is we give this value for the variables, whereas in Newman boundary condition we give the value for the derivative of the variable. So that is the difference. In addition to these two basic conditions, we have mixed boundary conditions, and like we give in certain regions we give Newman, certain regions we give Dirichlet. So those combination types are also available. And later on week 5, we have seen about the basic concepts of CFD, that is the finite difference approximation, how what types of approximations we are using, like in terms of forward difference, backward difference, central differencing schemes. And in week 6, it is about basic concepts of CFD using consistency, stability and convergence. And week 7, it is solutions of Navier-Stokes equations for compressible flows. And week 8, it is solution of Navier-Stokes equations for incompressible flows. So in compressible flows, we have a density to be varying, so we need not worry about too many things. So we used schemes like McCormack scheme, beam forming scheme to get the solution of Navier-Stokes for compressible flows. And in week 9, week 8, it was about incompressible flows. In incompressible flows, we had density to be constant. It was not varying. So we took the density out from the equation as common. So we had encountered additional difficulties. So we we had seen the newly proposed models like artificial compressibility method, stream function vorticity approach, pressure correction equation. So all those things we have seen in week 8. And in last week it was about the solution of linear algebraic equations using basic methods. And this week we'll see the solution of linear algebraic equations, advanced methods we will be seeing. And in the next week and the week later we will see about the finite volume method, including grid generation and turbulence modeling. So this is the 12 weeks course, and in today's class we will be seeing about the solution of linear algebraic equations using advanced methods. So what we have been doing, we are just we got the equations and we discretize the domain. We have the equation, we apply the equation, we convert those partial differential equations into algebraic equations. So these algebraic equations we need to get the solution. So this solution we will be using numerical methods. We are going to see about various methods that are implemented in CFD. Like, so many concepts have evolved from the start, and it makes the solution to the problems easier. Not all the methods that were developed are being used currently. Each method gave way to other method which had identified the issue with the previous method and proposed solution for this. So these are all to give you an idea. The many methods are given. You just need to get the basic understanding of the concepts involved. That is thing. And books and references, we have 5 books and references. The first one is Ferziger, J.H. and Beric M. 1999. Computational Methods for Fluid Dynamics, Springer, Berlin, Germany. And second one, it is Hirsch, C. 1988. Numerical Computation of Internal and External Flows, John Wiley and Sons, New York, USA. And it is Patankar, SV. 1980. Numerical Heat Transfer and Fluid Flow, Hemisphere, Washington, D.C., USA. And it is Verstig, H.K., Malalsekara, W. 1995. An Introduction to Computational Fluid Dynamics, the Finite Volume Method, Longman Scientific and Technical. Anderson, J.D. 1995. Computational Fluid Dynamics, the Basics with Applications, McGraw-Hill. So these are the 5 books for your reference. So I hope, like, by now you all are familiar with these course layout and books and references, and I hope most of you have utilized these books as well in your study. So now in today's class, as I mentioned, we are going to see about the solution of the linear solution to the linear algebraic equations using advanced methods. So we are almost nearing the end of our sessions. So this is week 10. We have 2 more weeks, and we'll see. So, and one announcement I would like to make: if you are having any doubts or any queries or any questions or any answers you want to say, I request you people to give me that in audio, like audio in the sense I want you to unmute yourself and tell me, because I may not look at the chat window during the session. It is not intentional. The thing is, if I go back and come here, sometimes I am getting stuck in the screen and it is making me lose the recorded video, and it is a bit tricky. So I need to have this video as well. So I request you people to unmute yourself and answer any questions, or if you have any queries also, please unmute yourself at any point of time. You can do, and you can ask the questions, or you can wait till the end of the session At that point, I'll look at the chat window and answer your queries at that time as well. In between, if you have anything, you can ask them. But if you want to wait till then, it is fine. But in the middle of the session, I may not look at the questions in the chat window. That is what I am trying to say. This is just a request to you people. Thank you. So now we will start. All right. So now this is question 1. What is it that we got in question 1? Question 1 is that which of the following statements is true about the alternating direction implicit scheme? Which of the following statements is true about the alternating direction implicit scheme? First one, it is an iterative method. Second one, it requires diagonal dominance for convergence. Third one, it can be applied to three-dimensional problems. So options are option A 1 and 2, option B 2 and 3, option C 1 and 3, option D 1, 2 and 3. So now we will look at what the statement is meaning about. The first one is stating that it is alternating direction implicit is an iterative method. So that is true because we are keeping one part of the equation as implicit and the other part of it we are keeping it as an explicit and we are solving. So if we have one equation, in that equation one direction we will keep it as explicit, another direction we will keep it as implicit for one equation, and in the next equation the one which was implicit earlier will become explicit and the one which was explicit earlier will become implicit. So that is how it got the name alternating direction. So it one direction, next direction, one direction, next direction, so it goes in that way. So it is an implicit, it is an iterative method, that is true, one is true. And second one, it requires diagonal dominance for convergence. So since it is an implicit method and we are going with solving it, we require diagonal dominance for convergence. So that is true. Third one, it can be applied to three-dimensional problems. This is also true. How? Because we are just keeping one direction implicit and the other explicit. So here it can be like one direction implicit, other two explicit. Again, out of the other two, we can take one implicit and keep the rest of the two as explicit and solve it. So again, the third one, the remaining one direction explicit and the other two implicit, and we will, one direction implicit and the other two explicit, and we will solve. So it can be applied to three-dimensional problems as well. Although we have seen the examples by utilizing the two-dimensional problem, alternating direction implicit scheme can be applied to three-dimensional problems as well. So this is, therefore answer is option D, that is 1, 2 and 3 is the right answer. Option D is the right answer. So first we will look at what alternating direction implicit scheme is. So it is in numerical linear algebra, the alternating direction implicit ADI method is an iterative method used to solve matrix equations. So in numerical linear algebra, ADA, that is alternating direction implicit, is an iterative method used to solve matrix equations. It takes advantage of the goodness of the tridiagonal matrix algorithm. So here we get the tridiagonal matrix algorithm goodness, like it takes from there and we get the solution. So we call it as it takes advantage of the goodness of the tridiagonal matrix algorithm. And lastly, it is about the scheme is expected to be faster than Gauss-Seidel method, but not as fast as the SOR method, optimal SOR method. So this scheme, that is alternating direction implicit, is observed to be faster than the Gauss-Seidel method, but not as fast as the Optimal SOR. Optimal SOR, when it is optimized with the correct parameters, it will give the fastest solution. But getting the optimal values for the SOR method is quite tricky and it is bit difficult. But other than that, if we get the proper thing, we can get the fastest solution. So that is one advantage of ADI over Gauss-Seidel method. So the last one is, if we take AX is equal to B, if we take AX is equal to B matrix, where A is the coefficient matrix, X is the unknowns, and B is the RHS vector or matrix, whatever. And then we are decomposing matrix A into A1 and A2. So in this form, if we decompose, we can put it in two equations. One is 1 plus tau 1 into A1 into xn plus 1 by 2 equal to 1 minus tau 1 into A2 into xn plus tau 1b. And the second equation is 1 plus tau 2 into A2 into x at n plus 1 time step equal to 1 minus tau 2 into A1 into x at n plus 1 by 2 time step plus tau 2b. So here what we are doing, we are decomposing A into A1 and A2 and rewriting it in two equations for us to get the solution. So first in this equation we are solving A1 implicitly, A2 explicitly. So here A1, if we see, we are going for the time step n plus 1 by 2 and A2 is being evaluated explicitly. Whereas in the next equation, what it becomes, A2 is evaluated implicitly, whereas A1 will be evaluated explicitly. A1 is evaluated explicitly, A2 part of this is being evaluated implicitly. So again, if we take AX is equal to B and then decompose it into A equal to A1 plus A2, we can put it in this particular form as 1 plus tau 1 into A1 into x at n plus half time step equal to 1 minus tau 1 into A2 into x at nth time step plus tau 1b. A2 part of this is being evaluated explicitly and A1 part of this is being evaluated implicitly. And the next equation is 1 plus tau 2 into A2 into x at n plus 1 equal to 1 minus tau 2 A1 into x at n plus 1 by 2 plus tau 2b. Here what we are doing, we are reversing it. A1 part of it is evaluated explicitly, whereas A2 part of it is being evaluated implicitly. So we are taking advantage of this decomposition and we are going alternating direction, one direction, next direction, one direction, next direction. So that is how it is being done. So that is known as alternating direction implicit method, which is an iterative method, and we can extend it to 3-dimension as well. So it is an iterative method. It requires diagonal dominance condition for convergence. That is true. It can be applied to 3-dimensional problems as well. So all three statements are in fact correct statements. So answer is option D, that is 1, 2 and 3. Now we are going to question 2. In question 2, what is being asked is that for the solution of AX is equal to B, which of the following decomposition of matrix A is the most implicit? For the solution of AX is equal to B, which of the following decomposition of matrix A is the most implicit? Options are LU decomposition, option B ILU, option C LU plus N as in SIP, option D LU plus N as in SIP. Okay, both are same. Option C and D are the same. So now what we are going to see is that when we are decomposing X is equal to B and we are decomposing the matrix A. So now in this decomposition, what are we observing? We are observing which one to be most implicit. So here first one is LU, second one is ILU, third one is LU plus N. So first one LU is the direct method, so that one is the most implicit method. LU being the direct method is the most implicit method. Second one ILU is incomplete LU decomposition, and that is actually, once again, that is actually more comparatively more implicit, but third one stones implicit is also comparatively more implicit than the incomplete LU decomposition method. So answer is actually option A is the right answer, because LU being the most direct method, being the direct method is the most implicit. So answer is option A, that is LU. So why LU is a direct method and ILU is not evaluated completely implicit and it requires iterations, and Stone 1968 proposed ILU decomposition which is more implicit than the conventional ILU. So here we are having three methods. First one is LU, ILU and LU plus N, as in Stone's incomplete LU decomposition that is proposed in 1968. So here LU is the direct method, so it is the most implicit. Second one, ILU, that is incomplete LU decomposition, is not evaluated completely implicitly and it requires iterations. So ILU is not completely implicit as well. But Stone in 1968 proposed an ILU decomposition which is more implicit than conventional traditional ILU, but not the most implicit. It is comparatively more implicit but not the most implicit. But LU being the direct method gives the most implicit solution. So that is the thing. So now we are going to question 3. Just read the question, I'll be back. Okay. So now in question 3, what is being asked is that advanced iterative techniques are used primarily to enhance which of the following aspects of basic iterative methods. Advanced iterative techniques are used primarily to enhance which of the following aspects of basic iterative methods. First one, it is convergence condition. Second one, it is convergence rate. And third one, it is ease of computation. So what are we doing? We are using advanced iterative techniques, right? Basically we have seen about advanced techniques only in this particular module, that is in this particular week's content. So that I hope you have all have watched the lecture video by the professor. So why are we going for the advanced iterative techniques? Advanced iterative techniques are used primarily to enhance which of the following aspects of the basic iterative methods. So we have basic methods. Why or what is the need for us to go to advanced iterative techniques? Is it convergence condition, or is it convergence rate, or third one ease of computation? So first one, if we talk about it, it is convergence condition. So yeah, that is true, because when we go with the higher or advanced techniques, we will get better convergence. And the second one, it is convergence rate. We will get a better convergence as I mentioned. And third one, it is ease of computation. That is not our ultimate aim, I would say. So if we look at the options, we have option A 1 and 2, option B 2 and 3, option C 1 and 3, option D 1, 2 and 3. So the answer is actually option A, that is convergence condition and convergence rate. Ease of computation is not our ultimate aim. We are to go for advanced iterative techniques, because we have basic methods and we have advanced methods. In fact, the advanced methods are very difficult to implement and get the solution. So it is not an easier thing. It is not easy to compute using advanced iterative techniques. Whereas with the basic iterative techniques, we will get better implementation. But the problem will be we will not get faster results. That is one thing. Sometimes we may not get the converged solution. For that only we go with higher order techniques like multi-grid method. Those are all the things that will come into picture. But basically we are going with the advanced iterative techniques to enhance without the following basic aspects of basic iterative methods. We are going with that to enhance the convergence condition and the convergence rate. So we are going with the advanced iterative techniques to deal with convergence condition and the convergence rate. I mean, we are not doing anything to go for ease of computation. In fact, even though like you will get the faster results by using advanced iterative techniques, we are not making the algorithm any easier. In fact, the algorithm will get complicated when we go from basic to advanced methods. So the ease of computation is not applicable here, but we want to get the ease of solution. But the motto or the purpose behind going for the advanced iterative techniques is not ease of computation, whereas it is for the convergence condition and the convergence rate. We want to get faster convergence and also we want to get the assurance for convergence. That thing is obtained or will be obtained through the advanced iterative techniques. So option A is the right answer. I hope it is clear. Advanced iterative techniques are primarily used to enhance the convergence rate and convergence condition of basic iterative methods. These techniques often involve sophisticated methods like preconditioning, accelerating techniques, or more complex iteration schemes to improve how quickly and reliably the method converges to a solution. So when we are going with advanced iterative techniques, what steps we follow in addition is that we do sometimes precondition or acceleration techniques will be implemented, or some more complex iteration schemes are being implemented to improve how quickly and reliably the converged solution we will get. Reliably the method converges to a solution. And while advanced techniques might sometimes simplify computations by reducing the number of iterations needed, their primary focus is not on simplifying the computation process itself, but rather on improving convergence properties. So this is what I mentioned, like when I said advanced techniques might lead to simplified computations in terms of reduced iterations, but the primary focus is not on that. It is on getting the improving the convergence properties. It is on getting the better convergence, because as I mentioned, these algorithms will not all the time be simple. Rather, it will be more complex and complicated. So we are doing techniques like preconditioning, accelerating techniques, or more complex iteration schemes. So why? Because we need to improve the chances for convergence. How quickly we'll get convergence and how uh, are we sure, how confident are we that we will get a converged solutions? So those things only we require ultimately. That condition and that rate is what is required when we are moving from basic iterative techniques to advanced iterative techniques. So that is the thing. Now we will go to next question. Question 4. Which of the following statements is true about the multigrid method for solving Ax is equal to B? I repeat the question. Which of the following statements is true about the multigrid method for solving Ax is equal to B? So multigrid method is one more advanced technique wherein we use a series of grids to get the solution, and below are few statements and we need to identify which one of them are true. So the first statement is that it uses multiple grids for the same domain. Second one, it uses multiple grids for the same equation. In the first one, it uses multiple grids for the same domain. Second one, it uses multiple grids for the same equation. So we are given two statements and we need to identify which of them are true. So in multigrid method, what we are doing, we are using a series of grids, finite grids to coexistent grids. So that too for the same domain. So we are using multiple grids for the same domain. That is, first statement is true. Second statement, we are using multiple grids for the same equation. Again, this is true because we are solving for the same equation only. So answer is option A 1 and 2, option B 1, option C 2, option D neither 1 nor 2. So the answer is actually option A 1 and 2 because we are using the same equation and same domain for the multiple grids. We are using multiple grids for the same equation. We are using multiple grids for the same domain. So we'll just quickly see what multigrid means. So in this slide I'll give you a brief idea. So in the later slide we will see more clearly. So we have one more problem related to multigrid problem. So we will see more in depth in there. In numerical analysis, a multigrid method or MG method is an algorithm for solving differential equations using a hierarchy of discretizations. As I mentioned, we will be solving using different sets of grids. We will be moving from finest grids to the coarsest grids. Hierarchy of discretization. They are very useful in problems exhibiting multiple scales of behavior. So why are we going with multigrids? We are going with multigrids because we need to damp the errors. Some problems will give you a scale of errors, will give you a range of errors behaving differently. So in those cases, multigrid method will be useful. For example, many basic relaxation methods exhibit different rates of convergence for short and long wavelength components, suggesting these different scales be treated differently. So long scale error, long wavelength, short wavelength error we will be getting. So if we solve it at different scales, it will be better for us to get the proper solution. So that's why we go for the multigrid method. The main idea of multigrid method is to accelerate the convergence of a basic iterative method. So if from basic iterative method we want to get a better convergence, so this is known as the relaxation, which generally reduces the short wavelength error by a global correction of the fine grid solution approximation from time to time, accomplished by solving a coarse problem. The main idea of multigrid method is to accelerate the convergence of a basic iterative method known as the relaxation, which generally reduces the short wavelength error by a global correction of the fine grid solution approximation from time to time, accomplished by solving a coarse problem. So we will see more in more detail in the last slides. The coarse problem, while cheaper to solve, is similar to the fine grid problem in that it also has short and long wavelength errors. So in each problem we will be having a series of errors. So we need to use approximate grid to get the appropriate solution. So that is what we are using in multigrid method. It can also be solved by a combination of relaxation and upper to still coarser grids. So we are using fine grids, moving to next further coarser grid, and finally it will be like coarsest grids. So in an iterative method, our ultimate aim is to reduce the residual. Residual is like x is equal to b we have, and x2 minus x1, something like that. The degree of non-satisfaction of the current solution with respect to that of the original governing equation, ax is equal to b. So when we are comparing our solution and the original governing equation solution, the residual should be almost very low, like that. If residual is high, it represents the degree of non-satisfaction of the current solution with respect to the original equation solution. So this is because there is some error in the solution. Why we are getting a different thing? Because we are getting some error in the solution. So this error can be decomposed into many components. As I mentioned, short wavelength component, long wavelength component, etc. Methods like Gauss-Seidel method is good at reducing error at the smallest scale, but it can't reduce the largest scale error. But the larger wavelength error are not damped down so easily in Gauss-Seidel method. We have to work on it many times before we damp it. So that is like computationally expensive and it is not required when we can do it at a different grid. So in multi-grid method, computation is started on a final grid. We perform few iterations, say 5 to 10, and we move on to the next comparatively larger grid, coarse grid. There again we do the error reduction, and some more iterations will be done here. Some of the long wavelength error which was not damped here would be damped here. And for again we will move on to even coarser grid. So which wavelength errors were not damped here will be damped here, and again we will move to the next coarser level. So likewise we will move on to further courses to grid. In each grid what we are doing only 10 iterations, and then we go to the next courses to grid, and by now we have reduced the error. This reduced error is used to improve the solution on the fine grid, and then we do some more calculations. So that is how we do the error reduction in the multi-grid method. So this is quite helpful for us when we are dealing with this. So what we are doing, we are solving for the same equation in the multiple grids, and we are solving for the same what was in the question, and we are using multiple grids for the same domain. We are using the multiple grids for the same equation. So both the statements are true statements only. So now that is for question 4. Now we are into question 5. In question 5 what we have is that if NP is the number of arithmetic operations for the multi-grid method, where n is the number of grid points, what is the value of P? So generally what we say for Gauss-Seidel method, we say we get the solution in n to the power of 2 arithmetic operations, and SOR, that is I'm talking about optimal SOR method, we say it to be less than the conventional Gauss-Seidel method. So it is like less than 1 point, and it would be like 1.5 something. So what is the value of arithmetic operations for the multi-grid method where n is the number of grid points? What is the value of P? So option A it is 1.1, option B it is 1.2, option C it is option C it is 2, option D it is 2.2. So answer is actually 1.1. number of arithmetic operations for the multigrid method is we are getting it at a low value, like we are getting it at a 1.1 operation itself. The number of arithmetic operations is comparatively lower in the multigrid method, that is we are using only n to the power of 1.1, whereas for the Gauss Seidel method it was n to the power of 2. The number of arithmetic operations only help us estimate the computational power requirement. So if it is low, it is better. The lower, the better. So here for the multigrid method, we are using multiple grids for the same solution, and we are performing 10 iterations in each of the grids. So the question is about the number of arithmetic operations for the multigrid method, given it as n to the power of p, and n is nothing but the number of grid points. So here answer is 1.1 is the right answer. For Gauss-Seidel method, again I am repeating, it is 2, and for optimal SOR method it is 1.5. But the issue in optimal SOR method is that parameters will not be known in general. So that is an issue there. Now we are going to next question. Okay. Now we have seen some basic sample problems. So from here we will be seeing some problems with regards to this particular statement. So here we are having figure A, B, C and D, and inside of that rectangular domain we have one smaller domain E, F, G, H. So we have A, B, C, D outer domain. Inside that we have one E, F, G, H domain. So the coming problems are based on this particular figure. So please take a look at it very carefully. You wish to solve the Poisson equation in the two-dimensional domain as shown in A, B, C and D. This is figure 10.1. The rectangular domain EFGH has a constant stores per unit area. So inside of this domain ABCD we have one smaller domain EFGH, which is the source term, which contains the source term per unit area. And it is given that AD has Newman boundary condition. So it is like we are giving some boundary with Newman boundary condition, that is the value of gradient is so and so. Whereas A, B, B, C, C, D are Dirichlet boundary condition. A, B, B, C, C, D are Dirichlet boundary condition. So we are using Newman boundary condition for A, D, and A, B, B, C, C, D. You use Dirichlet boundaries. You use uniform mesh and use a second order accurate discretization of the Poisson equation. You wish to solve the resulting set of linear algebraic equations which you have expressed in matrix form as Px is equal to Q. For this problem, answer the following questions. So what is given? We are asked to answer the following questions based on this particular problem statement. So we will read the problem statement again. We are given a domain AB, BC, CD, DA. That whole domain is AB, BC, CD, DA. I mean these are the lines composing the whole domain. Now this domain, that is ABCD, has 4 boundaries, and of that 4 we have one Newman boundary condition, that is inside AD. AD Newman boundary condition is like we can give it like an adibody boundary conditions, that is where we get the value as a 0, exchange value as 0, gradient value as 0, or we can give gradient value as something also, like whatever it is, we are not specifying it as 0, we are not specifying exactly as some value, but it is like a value to the derivative of the variable is what we are specifying. So along the side AD, so AD has Newman boundary condition, and remaining sides we have AB, BC and CD. In AB, BC, CD we are specifying the Dirichlet boundary condition. Now we are told that we are using uniform mesh and we are using a second order accurate discretization scheme for the Poisson equation, and now we need to solve the resulting set of linear algebraic equations, and that equation we have obtained, that linear algebraic equations we obtained after discretizing the Poisson equation. So we are solving the resulting set of linear algebraic equations, and we need to answer the following questions. So I hope the statement is clear. Just take a quick look at it, we will see this problem. Okay, now we will move on to the question actually. Okay, before that we will just see what is Poisson equation and what equation we are about to solve, just for your information. So Poisson equation is del square f, that is Poisson equation is given by del square f is equal to some function. So that function is a varies in x and y direction. So that is Poisson equation. So here we are taking it in the two dimension because the question in concern also has two dimensional problem only. Poisson equation in two dimensional form is given by dou square f by dou x square plus dou square f by dou y square equal to c of x comma y. Dou square f by dou x square plus dou square f by dou y square equal to c of x comma y. This is Poisson equation in two dimensional form, and we can discretize it in the second order form as f at I comma I minus 1 comma j minus 2 times of f of I plus f of I plus 1 comma j divided by delta x square plus f at I comma j minus 1 minus 2 times of f at I comma j plus f at I comma I plus I comma j plus 1. So here we are varying in the y x direction, here we are varying in the y direction, and this particular thing remains constant. I mean, it is a variable whatever, but we are not taking discretizing that. So this is varying with respect to x and y, but it will have certain values. So Poisson equation in two dimensional form is given by in general as del square f equal to f of x comma y. So here we are taking some constant c, which is a function of x and y in the right hand side, and on the left hand side we have dou square f by dou x square plus dou square f by dou y square equal to c into x comma y. So here it is f at I minus 1 comma j minus 2 times of f at I comma j plus f at I plus 1 comma j divided by delta x square plus f at I comma j plus 1 or j minus 1 minus 2 times of f at I comma j plus f at I comma j plus 1 divided by delta y square equal to c of x comma y. So that is a Poisson equation, and we are discretizing in the second order form. So using central difference scheme. So now we will go to the actual problem questions. That is question 6. We are into question 6 now. In question 6, what is given? Which of the following method can be used to solve px is equal to q from the above problem? Which of the following methods can be used to solve px is equal to q from the above problem? So Poisson equation we were given in the rectangular domain, and now we are asked which method can be used for solving that. First one, it is ADI method. Second one, it is ILU method. Third one, TDMA method. So ADA method is alternating direction implicit scheme, and we are having again a Poisson equation only, so it can be used. The alternating direction implicit method can be used. And the second one is ILU method or mm, ILU method, that is the incomplete LU method, wherein we decompose the matrix, and it is not an implicit method, but yeah, that is one. And the third one is TDMA method, that is Thomas algorithm or tridiagonal matrix algorithm. This is applicable when we have when we have the scope to form three diagonals, that is central, diagonal element and subdiagonal elements and super diagonal element, one above the diagonal and one below the diagonal. So we should have three rows, sparse matrix, three row matrix, not three row, three diagonal thing. So which can be used, one and two can be used. Second, third one we are not sure whether we will be getting. So we will see the answer. That is my answer. Option A 1 and 2, option B 1 and 3, option C 2 and 3, option D 1, 2 and 3. So answer is option A 1 and 2. As I mentioned, we are using. So which of the following methods can be used to solve Px is equal to Q? We are using ADA method and the ILU method. So in ADA method, so in ADA method, we are using the alternating direction implicit method, wherein we split the equation, that is coefficient matrix A into A1 and A2, and from that we will solve one direction implicitly, keeping the other explicit, and in the second split equation we will solve the other explicit and they keep the one implicit and the other implicit. So alternating direction it will move. So ADA method can be used, and the second one is that ILU method, incomplete LU decomposition method. So this method can also be used. So that is also one form of the method. And in the third one we have TDMA method, that is the tridiagonal matrix algorithm. In tridiagonal matrix algorithm, we need to have that three diagonal elements, one main diagonal, one subdiagonal and one above the diagonal element. So if we have that, we can use the TDMA algorithm, otherwise we can't use it. So we are not sure about it, so answer is false, because we are having it in a three-dimensional structure. Ours is dou square f by dou x square plus dou square f by dou y square. That form only we will have the Poisson equation. So the maximum number of elements which we can get goes up to 5. We are talking about two-dimensional and it can go up to 5. So the number of elements in a row can go up to 5 when we are talking about the internal cells. Along the boundary the number might be low, but in the cells it will be like minimum 5 will be there. I mean, not minimum, maximum 5 will be there. So we cannot have that tridiagonal structure. So the tridiagonal matrix structure we cannot get it here. So TDMA is false. So answer is therefore ADA method and the ILE method. Option A 1 and 2 is the right answer. Now question 7. In question 7 what we are having, which of the following methods cannot be used to solve Px is equal to Q from the above problem? Which of the following methods cannot be used to solve Px is equal to Q from the above problems? So here in the last question it was about which method can be used, but in this particular question it is about which method cannot be used. So what we have? We have first one SOR method, second one multigrid method, and third one SIP method. So SOR is like successive over relaxation method, and second one is multigrid method, and third one is SIP method. SIP method is Stone's implicit procedure, which Stone proposed in 1965 as a way of more implicit than the conventional implicit method. So here we are given three methods: SOR, multigrid and SIP, and all three can be used to solve for the above problem. We will look at the options once. Option A, 1, SOR method. Option B, 2, the multigrid method. Option C, 3, the SIP method. Option D, all three can be used. So answer is actually option D, all three can be used. So in previous question it was asked which of the method can be used. So in this particular question, the question is which method cannot be used. So while you are reading the question, read the question carefully. Here it is capitalized, each and every word of cannot is capitalized. But when you are sitting in the exam, read the question clearly once or twice before moving to answer, because you will be having a very short time limit and you will be under stress. But these things can be go unnoticed during exam because of a panic. So I request you all to stay calm during exam and read the question carefully so you can answer, because you know all the concepts, only you need to recollect them at that moment. So just stay stress free. Your preparation matters, and whatever result you are getting, it is like uh, that is fine. Like once you put the effort, you will have that satisfaction. So coming back, which of the following method cannot be used? So first one it is SOR method, second one multigrid method, third one SIP method. So all three method can be used. So answer is option D, that is all the three can be used. So that is for question 7. So actually the time now is 3:58. Let us all take a 5 minutes break and we will reassemble back by 4:03. Okay, we'll start, we'll continue. So, now we will see question 8. In question 8, what is being given is that which of the following statements is true about the source term in the region EFGH. So, in the problem statement, it was mentioned that there is a source term and that is in the region EFGH. So, in the figure, we have ABCD, and of that AD, that one side is Newman boundary condition. The rest, all three sides have Dirichlet boundary condition, and the source term in the equation is present inside the domain EFGH. So in question 8, it is about which of the following statements is true about the source term in the region EFGH. So first we look at it. First one, it strengthens the diagonal dominance of the discretized equation in the region. Second one, it affects the diagonal dominance of the discretized equation in the region. Third one, it affects the column vector Q. Okay, we have three statements first of all. First of all, where does this source term come? It goes in the del square f is equal to f of x comma y. So this source term will go into the RHS side of the equation. So it will not be coming or playing the role in the LHS side of the equation. So what we are doing, we are discretizing the equation Px is equal to Q. So the source term, if any present, will go to will be a constant value, constant or variable value, but it will be a value. So it will go into the Px is equal to Q. It will go into the right hand side vector, that is Q vector. It will not affect P or X. If it is not affecting P, we cannot say anything about how it is impacting the diagonal dominance condition. So here it is not affecting actually. It is not strengthening. It is not affecting the diagonal dominance of the discretized equation in the region. So answer is option. Third statement alone is the true statement. We will look at the options once, that is what are all the listed options, and we will arrive at our conclusion. Option A1, option B 2, option C 3, option D 1 and 3, option E 2 and 3. So now here in this question we are asked to find which of the following statements is true statement. So we know that first statement is false, second statement is also false, whereas the third statement, that is it affects the column vector Q, that is the true statement. So option C is the right answer, that is it affects the column vector Q. Answer is option C therefore, because if we go back and look at the questions, that is the problem statement, we will understand it more clearly. You wish to solve the Poisson equation in the two-dimensional domain shown in figure 10.1, that is this figure, wherein the rectangular domain EFGH has a constant source per unit area. So here it is constant source. It is not variable or it is not a function. So it in no way affects the diagonal dominance or even the matrix P, because it is a constant source per unit area. Side AD has Newman boundary condition and EB, BC, CD are Dirichlet boundaries. You use uniform mesh and use a second order accurate discretization of the Poisson equation. You wish to solve the resulting set of linear algebraic equations which you have expressed in the matrix form as Px is equal to Q. For this problem, answer the following questions. So Poisson equation in two-dimensional form, this we have seen. So now we are clear that the variation in the source term or anything that happens to source term only affects the column vector Q, because EFGH there is a constant source per unit area. So it affects only column vector Q. It does not strengthen the diagonal dominance of the discretized equation in the region. Similarly, it does not affect the diagonal dominance of the discretized equation in the region. And third, it affects the column vector Q. Third one is a true statement. Option C is the right answer. Now we will move on to question 9. In question 9, what is asked? Which of the following statements is true about the side EH? Which of the following statements is true about side EH? Dirichlet boundary condition is applicable on EH. Newman boundary condition is applicable on EH. Third one, Robin boundary condition is applicable on EH. No boundary condition is applicable on EH. So here, of all the statements given regarding side EH, we need to identify the correct statements. So, before knowing this, what do we know about boundary condition? Boundary condition are like the condition which we apply along the boundaries by specifying either the value to the variable or specifying value to the derivative of the variable. So in the former case, we call it as Dirichlet boundary condition, which is specifying value to the variable. Second case, it is Newman boundary condition. It is specifying value to the derivative of the variable. So that is what we call as boundary condition, and we have other combinations and mixed boundary condition, Robin boundary condition. Everything else stems from these two. Clear? We are clear in that. Now, where we apply boundary condition? We apply boundary condition at the boundaries. Whereas, if we go back and look at the problem, are we observing any boundary along EH? Along EH, we do not have boundaries, first of all. It is in the inside domain, and that domain has constant source per unit area. So this is a constant source per unit area. Entire EFGH is a constant source per unit area. We are not applying any boundary condition here in the inside domain, that is having a constant source per unit area. If this one is also a boundary, we need to apply boundary condition with regards to the question being asked. But in the question, it is clearly mentioned that the rectangular domain EFGH has a constant source per unit area. So we are not applying any boundaries, any boundary conditions. So the EFGH has a constant source per unit area. So it is not, we are not applying any boundaries. So if we go back and look at the question, we can now say that the last statement is the only true statement. No boundary condition is applicable on EH. EFGH as a whole is the constant source per unit area. So we are not giving any boundary conditions. Boundary conditions are not applicable in that region. Which of the following statements is true? We are not applying Dirichlet boundary condition. We are not applying Newman boundary condition. We are not applying Robin boundary condition. We are stating that no boundary condition is applicable on EH side. Alright, clear? So answer is option D. No boundary condition is applicable on EH. Now we are going to question 10. In question 10, what is being asked? Which of the following statements is true about the SOR method if the coefficient matrix is diagonally dominant? So which of the following statements is true about SOR method if the coefficient matrix is diagonally dominant? So what is SOR method? SOR method is successive over relaxation method. So we are given few statements and we are asked to identify which of the following statements are true with regards to the SOR method, that is successive over relaxation method. So we will see the statements first. First one, it's given that its convergence rate increases monotonically with the SOR parameter W. It is convergent if it is between 2 and 4. Its convergence rate is twice as much as that of Gauss-Seidel method. These are the three statements. Now, as I mentioned, right, we have the parameter in SOR, which is very difficult to get the proper parameter. But once we get the parameter, we can use it for anywhere and we will get the optimized solution. There is no doubt in that. But getting the optimal parameter of SOR is a tricky. So, which is not known in general case. So compared to SOR and Gauss-Seidel has n square number of operations, whereas optimal SOR has n to the power of 1.5 number of steps performed. So we look at the first statement. In SOR method, its convergent rate increases monotonically with the SOR parameter W. So as I mentioned, the getting the proper parameter value is tricky. And if it is the case, just imagine if it is a case of wherein we are increasing the convergence rate, we are increasing W and we are able to get the increased convergence rate. Imagine that would be better. But that is not the case because as I mentioned, it is difficult to get the value of W. If we are using that now, we can give the maximum value of W and we can get the converged rate easily. But are we able to do that? We are not able to do that. So first statement is false statement. Its convergent rate increases monotonically with SOR parameter W. It is false. Rather, we are not able to get a proper relation between those two. And second one, it is convergent if W is between 2 and 4. Again, this is false because it should be less than 2 actually for it to be convergent. And third one, its convergent rate is twice as much as that of Gauss-Seidel method. That is also actually false, I guess. So we will see the solution options first. Option A 1, option B 2, option C 3, option D 1 and 3, option E none of the above. So we are asked to identify which of the given statements is true about SOR method, and we have identified that none of the above is true statement with regards to the SOR method. So option E is the right answer. None of the above. So how we will see? Successive over relaxation SOR method, as long as omega is between 0 and 2, convergence is assured. As I mentioned now, it is like less than 2, we will get the assurance for convergence. And if it is like the rate of convergence is varying, which depends as before on the spectral radius of the new iteration matrix. So these are all the concepts you have seen in the theory. The rate of convergence is varying, and which again depends on the spectral radius of the new iteration. As long as omega is between 0 and 2, convergence is assured. The rate of convergence is varying, which depends on the spectral radius of the new iteration matrix. Omega, I mentioned it as W, but it is omega, fine, whichever. Omega varies between 1 and 2 for case of over relaxation, and rate of convergence does not vary monotonically between 1 and 2. Like if it is 1 and 2, right, if we increase from 1, 1.1, 1.2, with every increase our rate of convergence should also increase. But are we observing that? We are not observing that, right? So the rate of conversion does not vary monotonically between 1 and 2 as well. Typically, it goes through a minimum or the number of iterations needed to reduce a residual by a factor of 10. That value is asymptotically convergence rate. So it goes through a minimum or the number of iterations needed to reduce a residual by a factor of 10. So that is the asymptotically convergence rate. It reduces as omega increases, it goes to a minimum and then it starts again coming back up. So uh, so it reduces as omega is increased. As we increase the omega, right, it reduces, then it goes to a minimum and then it starts coming back like a minima curve. It reduces, it goes to a minimum and then it starts coming back up. So that means there is an optimum value of omega. Like here you are able to see that, right? Like my cursor is pointing. It reduces, it goes to a minimum and then it starts coming back. So we have an optimum value of omega for which there is the minimum. And this is the optimum value of SOR for the given SOR method. This optimum value will have the least number of iteration steps needed to reduce the residual by the factor of 10, and also it has the highest convergent rate. So I hope it is clear. As long as omega is between 0 and 2, convergence is assured. The rate of convergence is varying, which depends on the spectral radius of the new iteration matrix. Omega varies between 1 and 2 for the case of over relaxation, but the rate of convergence does not vary monotonically between 1 and 2. Typically, it goes through a minimum of the number of iterations needed to reduce a residual by a factor of 10. That value is asymptotically convergence rate. It reduces as omega is increased. It goes to a minimum and then it starts coming back up. So that means there is an optimum value of omega for a given matrix and for a given SOR method. Here it refers to the rate of convergence. This optimum value will have the least number of iteration steps. That is, this optimum value of omega will have the least convergence rate. Sorry, will have the least number of iteration steps needed to reduce the residual by a factor of 10 and has the highest convergence rate. Alright. Now we will go to next question, that is question 11. In question 11, what do we got? Which of the following statements is true regarding the number of floating point operations per iteration in the SOR method compared to Gauss-Seidel method? Which of the following statements is true regarding the number of floating point operations per iteration? For per iteration, the number of floating point operations in the SOR method compared to the Gauss-Seidel method. Option A. The SOR method requires significantly more floating point operations. Second one, SOR method requires significantly fewer floating point operations. Third one, SOR method requires exactly twice as many floating point operations. Option D, none of the above. So SOR method and the Gauss-Seidel method, when we are comparing both the method with regards to the number of floating point operations, they are almost the same. The SOR method requires almost the same number of floating point operations as in the Gauss-Seidel method. It is not given here, so answer is option D, none of the above. Option D, none of the above is the right answer, because SOR method requires almost the same as many floating point operations as in the Gauss-Seidel method. Whereas in the options it is given that SOR method requires significantly more number of floating point operations. That is false. It does not require significantly more number of floating point operations. Similarly, second one, it is mentioned that SOR method requires significantly fewer floating point operations. Again, that is false. Third one is also false. SOR method requires exactly twice as many floating point operations. That is also false, because it is not more or less or twice as many the exact values. Whereas the correct answer is that SOR method requires almost the same as many floating point operations. So option D, none of the above is the right answer for this particular question. SOR method requires almost the same as many floating point operations. Alright. Now we will move to next question, that is question 12. In question 12, we are asked that the ADI method for the solution of AX is equal to B is based on the decomposition of dash. The ADI method for the solution of AX is equal to B is based on the decomposition of dash. That is a question. So here what are we doing in ADA method? We already seen that ADA is an alternating direction implicit method in which we will split or decompose the coefficient matrix A into A1 and A2 for the two-dimensional problem I am talking about, and we will use two set of equations. In the first one will be matrix will be solved explicitly, one will be solved implicitly. Second, it will be reversed, and the one which was solved as implicitly in the previous equation will be solved explicitly, and the one which was solved explicitly in the previous thing will be solved implicitly here. So that is known as alternating direction. We are alternating direction implicit. One time we are using one equation implicit, one direction. The next time we are using other direction implicit. So it is alternating direction implicit method. For the solution of Ax is equal to B is based on the decomposition of dash. Option A, matrix A into M plus N. Option B, the problem into an upper triangular matrix problems. Option C, matrix A approximately into LU. Option C, option D, none of the above. So matrix A into we are decomposing the matrix A into A1 and A2. We are not actually going very directly as M and N. For example, in M and N, what we will be doing, we will be using xk equal to M into x at k minus 1 iteration plus N. So we indirectly divide it as that. And here we are not doing that, rather we are dividing I mean to say we are not exactly splitting the A matrix into M and N. Even though we are constructing M and N, similar thing here in the ADI method, we are not directly splitting matrix A into M and N. Rather, the whole equation Ax is equal to B is being converted into other form before being split into the M plus N form. So, option A is not the right answer. Similarly, option B and C are not the right answer. So answer is none of the above. Why? Because we are splitting matrix A if we want to have it directly A1 and A2 and solve it in the alternating direction. That is the more straightforward manner. If we go with M and N form, we are not splitting A directly into M and N. Rather, it goes through other series of steps and finally we will be getting. So answer is therefore none of the above is the right answer. In numerical linear algebra, the alternating direction implicit method, ADI method, is an iterative method used to solve the matrix equations. It takes advantage of the goodness of the tridiagonal matrix algorithm. This scheme is expected to be faster than Gauss-Seidel method but not as fast as the optimal SOR method. If we take Ax is equal to B, and here that is what I have mentioned, we are decomposing A into A1 and A2, A equal to A1 plus A2, we can put it in this particular form, 1 plus tau 1 into A1 into x at n plus 1 by 2 equal to 1 minus tau 1 into A2 into x at nth iteration plus tau 1b. Here we are using n plus half time step. So this A1 part is being treated implicitly. A2 part is treated explicitly. A2 part of this is being evaluated explicitly and A1 part of this is being evaluated implicitly. In the next step, what will happen? We will reverse the direction. So it will become 1 plus tau 2 into A2. Here A2 comes here into x at n plus 1th time step equal to 1 minus tau 2 into A1 into x at n plus half time step plus tau 2b. Here this is evaluated explicitly, that is A1 is evaluated explicitly, A2 is evaluated implicitly. Here we are going to n plus 1th time step. So A1 part of this is being evaluated explicitly, A2 part of this is being evaluated implicitly. So answer is none of the above is the right answer. If we go back and look at the question, ADI method for the solution of Ax is equal to B is based on the decomposition of matrix A into M and M plus N, matrix A approximately into LU, problem into an upper triangular matrix problems. So all these are false statements. So answer is option D, that is none of the above is the right answer. I hope you are clear with this question. So we will go to next question actually. That is question 13. In question 13, what is asked is that in the SIP method is Stone's implicit procedure that was given in I guess in 1968. Stone's SIP procedure for the solution of Ax is equal to B, matrix A is decomposed into dash. Option A, LU. Option B, ILU. Option C, LU plus N. Option D, none of the above. So answer is actually option C, LU plus N is the right answer. Stone's implicit procedure wherein we split the matrix A into LU plus N. So here it is given in 1968. Stone in 1968 proposed an ILU decomposition which is more implicit than the conventional LU. So what happens is that so in general, if we are dividing the matrix into n, m and n, right? What we do, m into phi at k plus 1 equal to n into phi at k plus b, right? That is how we split. So the construction of m and n, m into phi plus k plus 1 at, I'm sorry, m into phi at k plus 1 equal to n into phi at k plus b. The construction of m and n is difficult in few, easier in few. For example, in Jacobi and Gauss-Seidel SOR method, the construction of m and n is effective, m and n is easy, and evaluating phi at k plus 1 from the phi at k is also easy. But the iterating schemes, will it converge fast? It won't converge fast. So that was an issue. So in order to make the decomposition relatively easier and relatively easy to perform, Stone's implicit procedure was introduced, wherein that m which we are giving, ax is equal to b, we are putting in m into phi at k plus 1th iteration equal to n into phi at kth iteration plus b, that form, right? So here Stone proposed that to make the decomposition relatively easy, they produced m with more of a, more like a, and n that contains less of a, that is the matter. More of a and n that is less of a. After that, which the m that contains more of a is like decomposed into Lu, and it goes to that other iteration. So it is like Lu plus n. So that is how it is done. So basically, Stone's implicit procedure for the solution of Ax is equal to b for matrix A is decomposed into Lu plus n. So option C is the right answer. I hope it is clear. So okay, now we are going to see about multigrid method problems. So as I mentioned previously that we will be seeing more multigrid, how it is used, we will see now. Okay. Multigrid method. In numerical analysis, a multigrid method is an algorithm for solving differential equation using hierarchy of discretization. What do we mean by hierarchy of discretization? We are using series of grids, from finer grids to coarser grids to coarsest grids. So that is known as hierarchy of discretization. So we are using multigrid method. It is an algorithm for solving differential equation using hierarchy of discretization. And second one, they are very useful in problems exhibiting multiple scales of behaviors. For example, in a single problem, you will be having a series of errors like small wavelength error, large wavelength error, like small wavelength or high frequency errors, large wavelength or low frequency errors. In what happens is that in fine grids you will be able to damp the small wavelength errors, that is the high frequency errors, very well, but you won't be able to damp the large wavelength errors in the smaller grids. So you will move to the next grid and you will damp that. That is the idea. So basically now we will forget all that. We will just remember that in a single problem itself we will be having multiple scales of behaviors, multiple error scales, which we can't damp using a single grids. For example, many basic relaxation methods exhibit different rates of convergence for short and long wavelength components, suggesting these different scales be treated differently. The main idea of multigrid method is to accelerate the convergence of a basic iterative method and known as relaxation, which generally reduces the short wavelength error. So what happens is that why we are going with multigrid is that to accelerate the convergence rate. from a basic iterative method. In basic iterative method, we reduce the short wavelength error. So here we are reducing it, and by using a global correction of fine grit solution approximation from time to time, we are accomplished by solving a coarser problem. The coarse problem, while it is cheaper to solve, is similar to the fine grit problem in that it also has short and long wavelength errors. So in coarser problems easier to solve, but it again has the smaller and long wavelength errors. So accordingly we will have a series of grids and we will solve or damp the errors in those grids, and we will pass the solution back into the final grid. That is what we basically do. It can also be solved by a combination of relaxation and appeal to still coarser grids. We go to further coarser grids. So in an iterative, these two slides are just repetitive from that problem, but here I am just giving you a more understanding. I hope if you have any doubts, please feel free to stop me and we can discuss that. In an iterative method, what we were talking about is that we are trying to reduce the residual. Our ultimate aim is to reduce the residual. Residual is nothing but which we get from the our solution with respect to the original governing equation Ax is equal to b. That is the difference between those two. The degree of non-satisfaction of the current solution with respect to that of the original solution. Original equation Ax is equal to b. So we are trying to do that. Basically in all the problems we are trying to do that. This is because there is some error, we are getting some residual. There is error, we are getting some residual. The error can be decomposed into many forms like short wavelength error and high frequency errors, or large wavelength and low frequency errors. So like some methods will be very good at reducing the smaller wavelength, smallest scale errors. Like fine grids, we can solve finer small wavelength errors, but it cannot damp the large wavelength errors. Similarly, Gauss-Seidel method is good at reducing the error at the smallest scale of error, but the larger wavelength errors are not damped so easily in the Gauss-Seidel method. We have to work on it many times before we can damp it. The computation is actually started on a finer grid. We carry out fewer number of iterations, say 10 iterations, and we pass the error from the finer grid to the next coarser grid. Finer grid to coarse grid. Then we again do some iterations in that coarse grid, and we will have some wavelength errors. Some of the longer wavelength error which was not damped in this fine grid will be damped here. Still we will be left out with some errors. So again we will take this error to the next coarser grid, even coarser grid, so that with error which was not damped here will be damped here. And then it is moved to further coarser grid and finally coarsest grid also, wherein we will be damping out all the errors. In each grid we are doing only 10 iterations, and then we go to the coarsest grid. Now we have reduced error. This reduced error is used to improve the solution on the fine grid. And we do some more calculation. So we are going from final grid to coarser grids, wherein we are reducing the errors, and after that we are using that error to improve the solution on the final grid. After reducing the error, we pass it on to the finest grid and we do some more calculation where we are improving the solution. That is the idea behind the multi-grid method. So most of the concepts you would have seen in the lecture itself. So here we are just transferring the solution through a succession of finer measures to be accurate at higher frequencies. As I mentioned now, we will get that afterwards. So that is the idea behind using the multigrid approach. Hope it is clear. If you have any doubts, you can ask. Now we are into question 14 actually. In question 14, what we got, which of the following statements is true about the multigrid method of solving Ax is equal to B? So previous thing itself we have seen that we will be solving multiple equations. We will be using multiple grids for the same domain and multiple grids for the same equation. But now we will see what statements are given over here. Which of the following statements is true about the multigrid method for solving Ax is equal to B? First one, it uses the same boundary condition on all the grids. Second one, it uses different boundary condition on all the grids. So we know that it uses the same conditions. We are not using any different conditions in the multiple grids. So as we move from finer grid to coarser grid, we are not changing any boundary conditions. So similarly, we are using only same boundary conditions, same equations, same domain, everything same. So which of the following statements is true about the multigrid method of solving Ax is equal to B? It uses the same boundary condition on all the grids. So option 1, statement 1 is the right statement, whereas the second statement, which is mentioning that it uses different boundary condition on all the grids, is a false statement. That is not the true statement. We will see the options now. Option A 1 and 2, option B 2, option C 1, option D 1 and 2. It should be neither 1 nor 2, but your answer is option C is the right answer because it uses the same boundary condition on all the grids. We will change the statements, neither 1 nor 2. So option C, that is it uses the same boundary condition on all the grids, is the right answer. Now we will go to question 15, that is the last question for today's session. It is also again about multigrid method. Multigrid method is efficient in solving Ax is equal to B because dash. Option A. Okay, again we are given few statements. First one, only part of the computations are solved on the grid. Second one, computation on coarser grids takes less computational time. Option A 1, option B 2, option C neither 1 nor 2, option D both 1 and 2. So the answer is actually option D, that is 1 and 2 is the right answer. Why? Because what is multigrid? Multigrid method is like we are going from finer grid to coarser grid. So in each grid we are damping out the concerned error, like one small wavelength error we are solving in finer mesh, and the next larger wavelength error we are solving in the next larger grid, and in the further larger grid we are solving the further larger wavelength errors. So only part of the computations are being solved on that grid size. So first statement is true. Only part of the computations are solved on the grid. Second one, computation on coarser grids take less computational time. That is also true, right? In a coarser grid, we will take less computational time because the number of grids in the coarser domain coarser grid size will be low. The number of grids will be low. So it takes less computational time. Whereas in the finer grid, what happens, we will have a large number of cells, so many cells. So computation on so many cells will take time. That number of, I mean, all will be depending on the mesh number, right? Number of cells. So if spine mesh we are using, the number of cells will be large. So computation time will also be large because we are solving the equations on each cells. But if it is a coarser mesh, the number of cells in the domain will be less, and therefore the computation time will be low because the number of cells is low. The second statement is also true. So both 1 and 2 statements are true. So answer is option D, that is 1 and 2 is the right answer. Multigrid method is efficient in solving Ax is equal to B because only part of the computations are solved on the grid, and second one, computation on coarser grid takes less computational time. So both 1 and 2 are right answer. So yeah, option D is the right answer. Well, that is the last problem for today's class. Thank you for attending today's sessions. If you have any doubts, you can ask me now. We have some 10 minutes time. Okay, in the meantime, I'll just give you a quick recap of what we have seen in today's class. Not everything, just a recap. So in today's class, we have seen about the advanced methods to solve the linear algebraic equations. Of that, mostly we have focused on alternating direction implicit scheme and also Stone's implicit procedure. And finally, multigrid method, we have seen two problems. So multigrid method we have seen quite fully, I hope. So I think it covered you all. SOR method, optimal SOR method, and we have seen about alternating direction implicit scheme. So this is how one part of it is being solved implicitly, the other part is solved explicitly. So we are going from one direction to the other implicitly. Implicit solution is carried from one direction to the other, so it is known as alternating direction implicit scheme. It can be used for 3-dimension as well. So again, we have seen about the multigrid method, and advanced iterative techniques are used to have a better convergence condition and convergence rate. And apart from that, we have seen more detail about multigrid method, wherein we observe that we are going from finer grid to coarser grid to further coarser grid. Why? Because only then we can damp the large wavelength error, which will not be damped at the finer grids. So we are just solving the same equation in all the domains. I mean in all the grids, not in domains. Same domain, same equation in all grids. Just it will be beneficial in damping out the large frequency, large wavelength errors and small frequency errors. High frequency error can be damped out in fine mesh itself. So that is why we are going for multigrid method. So that we have seen. And we have seen about a problem wherein we had a source term and we solved the Poisson equation in this. And relating to it, we have seen which method can be used. ADA, ILU can be used. TDMA we can't use because it is a two-dimensional grid problem. We will have 5 elements in one equation in the inside domain. Inside the domain, in the interior grid, we will have 5 elements in the equation. So we cannot get the tridiagonal mesh structure, I mean tridiagonal matrix structure, so we cannot use tridiagonal matrix algorithm. So that is the thing. Other than that, we can use SOR multigrid SIP method. So also the source term in this particular question affects the column vector only. It is not contributing in any way to the discretized equations diagonal dominance condition. And we have seen about successive over relaxation method, wherein it gives convergence between 0 and 2. If it is greater than 1 and between less than 2, it is known as over relaxation. And as omega is increased, it goes to a minimum and it starts coming up again as omega is increased. So we have an optimum value for omega, and for the given SOR method, which will have the least number of iteration steps to reduce the residual by a factor of 10, and that has the highest convergence rate. So we have seen about that, and SOR method requires the same number of floating point operation as the Gauss-Seidel method, and ADI method again is Stone's implicit procedure and multigrid method. So yeah, that's it for today's class. And if you have any doubts, you can always ask either through the NPTEL online forum, or you can also post it below this video wherein I can answer your queries. So yeah, thank you for attending today's class. We will meet again next week at the same time, 3 p.m. to 5 p.m., wherein we will discuss problems relating to the next week's solution. And yeah, that's it. Anything else? Yeah, these lecture videos and the lecture PPTs will be available to you. You can use it anytime. So this will be given in the, I mean, the video link will be given, and the PDFs are being uploaded in a Google Drive. The link for which is also given. Both of that is given in the course website under problem solving session. There, the link is Excel sheet is there. Every week, that link is being updated, so you can use it as well for any of your queries. So yeah, that's it for today's class. Thank you so much for attending today's session. And if there are no doubts, I would like to close today's session. So this is one of the shortest sessions, I guess, wherein we are stopping at 3:56 itself. All right. Thank you. We'll meet next week. Thank you. I'm closing the session.